Hello everyone, this is Akang Suman here. Now we are going to start the next chapter, that is dynamic analysis of the single slider crank mechanisms. We have seen in the first chapter simple mechanisms that we have classified three categories. The first is 4-bar chain, the second is single slider crank mechanisms, and the third is double slider crank mechanisms. So in all the three simple mechanisms, there are 4 links and 4 joints. Okay, and if I'm talking about the single slider crank mechanisms, out of 4 joints, out of 4 pairs, one is sliding pair and the remaining 3 are turning pairs. Okay, this is the single slider crank mechanisms. The number of links are 4. Okay, and if I'm talking about the pairs, turning pairs, there are 3 turning pairs and the one is sliding pairs. That's why its name is single slider crank mechanisms. Okay, so in the dynamic analysis we will consider the forces acting on the single slider crank mechanisms parts. Okay, so let me introduce. In the introduction part, we will see different types of terms that is going to be used in the dynamic analysis. Okay, so inertia of the collecting rod is not considered in this analysis. Okay, so let me draw the diagram. Here you can see this is a single slider crank mechanisms. Okay, in which a cylinder is going to be sliding in a sliding motions, and there is a crank which is going to be rotated here. Okay, so this is our crank, this is collecting rod. Here I am just named it, that is collecting rod, and that is a crank, and this is piston. Okay, this is piston. So there will be a length of the connecting rod that is denoted as L, and if the radius of rotation of the crank is small r, so I'm just writing here L is the length of the connecting rod. It is the length of connecting rod, and the r is the radius of crank. You just have to know what term denotes the length of which link. Radius of crank. Okay, and there is a mass of the reciprocating parts. Small m denotes the mass of reciprocating parts. We will do the numerical questions based on the dynamic analysis, because the number of numerical questions is going to be asked from this topic, from this chapter. Mass of the reciprocating parts. Okay, and if I'm talking about the obliquity ratio, that is important. How to calculate the obliquity ratio? Obliquity ratio is denoted as N is equal to L upon R. This is the obliquity ratio formula. N is equal to L plus R. Here you can see that we know that the length of the connecting rod is greater than the radius of rotation. Okay, so N will be greater than 1. Okay, and it is having the large value. It is having the large value. This is the obliquity ratio. N is equal to L plus R. In the numerical questions, you will see that number of in every questions you have to find out the value of obliquity ratio. So if there is an angle, if this is a crank which is going to be rotated, and this is known as the inner dead center. This position is known as the inner dead center. Inner dead center means theta is calculated from inner dead center. Theta is calculated from inner dead center, and here this is the theta, which is angle turned by the crank from inner dead center, or you can call it as top dead center. This is sometimes called it as the top dead center. So here I am writing that theta denotes the angle turned by the crank. Angle turned by the crank. Angle turned by the crank from inner dead center or top dead center. Okay, from inner dead center or top dead center. This is the angle turned by the crank. Okay, now if I'm talking about the angle turned by the crank, we all know that omega is equal to d theta by dt. Omega is equal to d theta by dt. So what will be the omega? Omega will be the angular velocity of the crank. So this will be the angular velocity of the crank. It will be omega is the angular velocity of the crank. Okay, so you can see here, if this is the theta, if this is angle theta, we can draw a perpendicular here, and when we draw the perpendicular, what we will get, this is the perpendicular, okay, 90 degree, okay, and this is r, we all know. So this means this angle, if this angle is theta, that means it would be r sin theta, yes or no? If this is a, if this is a, this is o, this would be m. M is the perpendicular, we have drawn that, and it would be r sin theta. And if there is a theta angle when the crank is rotated, there will be also rotation of the connecting rod, okay, with the horizontal. So I am considering this angle is beta. Okay, so if this is 90 degree, okay, this is perpendicular to the horizontal, that means it would be r sin theta, and it would also be, if you consider this triangle, it would also be L sin beta. So I can write here that AM is equal to L sin beta. This is also equal to R sin theta. Okay, you can see in the diagram here, this is R sin theta and this is L sin theta. So this is the relation you will get, L sin theta, L sin beta is equal to R sin theta. So from here, if I write the sin beta in terms of theta, what we will get, R upon L sin theta. Okay, so R upon L, the L upon R is the obliquity ratio, so I can write here sin theta upon N, yes or no? So what we will get, that sin beta is equal to sin theta upon N. And if I going to find out the value of cos beta, then how can we calculate cos beta? We all know that cos beta will be equal to under root of 1 minus, since we know that cos beta is equal to 1 minus sin square beta, then we can calculate the value of cos beta also. This would be helpful when we calculate the piston motion, velocity and acceleration of the connecting rod also, that will required there. Okay, so this would be under root of 1 minus sin square theta upon N square. Okay, so this is the relation. You must understand how we have calculated the cos beta value. And first important thing you must remember, if you don't know, if you don't want to remember this, you just have to remember these equations, this relation. This is very important. Okay, and in the diagram I have shown you how can we put them equal to L sin theta is equal to R sin theta, L sin beta is equal to R sin theta, L sin beta is equal to R sin theta, because this AM is common length for both the triangles, so it would be equal. Okay, that means if I'm to consider this triangle, this bigger triangle, that would be L sin beta. If I consider this small triangle, that would be R sin theta. So both will be equal to each other. So finally we all know that length of the connecting rod upon the radius, that means the ratio of length of the connecting rod upon the radius of crank, that would be considered as the obliquity ratio. Okay, so if you want to calculate the beta, that means we know in the question there will be theta value given. So if you want to calculate the value of beta, how can we calculate? You have to apply this relation. Okay, either you can learn directly in terms of sin beta or cos beta, or if you don't want to, if you are not able to remember this directly, you just have to remember this thing. Okay, so this was the introduction part of the chapter, in which we have seen the obliquity ratio and the relations between beta and theta. Now we will start with the kinematic analysis, and finally we will complete this chapter at the end of the dynamic analysis. Okay, so in the kinematic analysis generally we will study about the velocity, accelerations and the piston motions, and in the dynamic analysis, that is important, that is the core part of the chapter, we will study what types of forces is working in the single slider crank mechanisms. Okay, so thank you.